Now, today, we're going to move on to the geometry of linear algebra, the geometric view. This is actually where the fun begins. This is where you will begin to see how linear algebra is useful and relevant to computer science and machine learning. A lot of the algorithms that you love and use come out of the ideas starting from vector spaces. Even things like ChatGPT is done by thinking of words as though they're embedded in a space, a vector space of meanings. So we start talking about vector spaces, bases, and dimensions. But before doing that, we will start by reviewing linear combinations because that's at the core of what we will be talking about starting today. So linear combination is a simple idea. Right in the first class, we saw that vectors could be scaled. Every vector in Rn. For every vector in Rn, if I give you a scalar that is a member of R, then that scalar times that vector is a member of Rn. Meaning you take a vector, scale it by a number, and that is still a vector. The vector space, which is the set of all vectors of a given dimension, is closed under the operation of scaling. That's what it means. So I use this term vector space without actually having defined it, but don't worry, we will define it later today. Similarly, vectors can be added. So if you have two vectors in Rn, you add them, you get another vector in Rn. Rn is just the set of all possible vectors of n dimensions and components that are real. R for real, n for the number of components. So nothing prevents us from doing both these operations at the same time. So you can scale and add. So if you have two vectors, x1 and x2 in Rn, and two scalars, s1 and s2 in R, then a new vector, z, equal to s1x1 plus s2x2 is a member of Rn. It is closed under the operation of taking the linear combination 2. And that thing that you see there, z, is the linear combination. Well, it's one linear combination. Let me give you one more, a bit more complicated one. So instead of taking just one pair of vectors in Rn, suppose you take k vectors. K can be anything more than 0 really. K vectors of the kind xi in Rn and k scalars of the kind si in R. Then z, which is a sum with I, the index running from 1 to k, si xi, and that linear combination also will be in Rn, meaning that complicated linear combination also is a member of Rn. Any kind of linear combination that you can think of will still be in the set of all possible vectors of the same number of elements over the same field. And that basically means that vector space, that set, is closed under the operation of taking linear combinations of any kind. So this is what we mean by a linear combination Z. So to reiterate, Z is a vector in Rn, so the set Rn being a set of all possible vectors of n real elements is closed under the process of taking linear combinations. Now let's see this in action. Let's just take two vectors in R2. So n now is just 2. I have my first vector and the second vector, the red one and the blue one. We saw this a long time ago, and we can add them, which is like taking linear combination of the two vectors with unit weightages, or you can take some other random weightages that you see there. So S11 and S22 were just 1, S21 and S22 were some other numbers. You take the red vector, scale it by S21, you get this scale version, which is a vector in R2. You take X2, scale it by S22, which is some number. So that happens to be a negative number, so you get some other vector here, but in the same line as X2. You add them up by taking this vector over to the tip of that scale version, and then you get a point here. And you can keep doing it. The point is, given any green vector at all in R2, you can always find some scaling factors Sn1 and Sn2 that will scale x1 and x2 so that you get that particular vector. This is what we will mean later by saying that x1 and x2 spans the vector space of R2. To say it once more, any vector at all that is a member of R2 can be expressed as a linear combination of x1 and x2, and that's what it means. I understand that I'm using the terms linearly independent and span without having defined them. So let me do that now. Linear independence of vectors basically means that if you have k vectors, none of them can be written as a linear combination of the rest. That means you take one vector out of k, try to express it as a linear combination of the rest of them. You will not be able to do that. That is what linearly independent means. In the case of R2, if you have two vectors that are not on top of each other, you cannot write the second one, my blue vector, as a scaled version of my first red vector. That means they are linearly independent. Span all of R2 means any vector in R2 can be written as a unique linear combination. The uniqueness is important, and it is kind of obvious because if I give you two vectors, my blue vector and my red vector, and I give you two specific scalars, if you scale them and add them, you can see that there's only one vector that you will get. Similarly, if you start from one vector, there are only two specific unique scalars that you can come up with, so that these two vectors, the blue one and the red one, will scale and add to give me that green vector. You saw this actually earlier, and you will see that again a bit later today. What that means in the case of R2 is that two linearly independent vectors are necessary and sufficient to span all of R2 or to express any other vector in R2 as a linear combination. Similarly, n linearly independent vectors are enough and necessary to span all of Rn. If you have one extra vector, that is, if you have n plus 1 vectors in Rn, at least one of the n plus 1 vectors will have to be linearly dependent. Can you prove that? Actually, by now we have the knowledge necessary to go ahead and prove it. It's actually fairly simple. All you have to do is to put these n plus 1 vectors in a matrix as columns. So what's the size of this matrix? You have each vector in Rn, so each vector has n components, so number of rows in this matrix will be n, and you're putting n plus 1 vectors as columns, so you have n plus 1 columns. What's the rank of this matrix? What's the maximum rank this matrix could possibly have? It's got only n rows, so it cannot have more than n pivots, so it can have only n pivots, so the rank, the maximum possible rank is n. It could be less than that, but the maximum is that. What does rank mean in a different context? Rank is a number of linearly independent rows or columns. So how many linearly independent columns are there in this matrix? Without knowing anything about the nature of these vectors, you can already say that you cannot have n plus 1 vectors that are linearly independent, because the rank is the number of linearly independent vectors. It can have only rank n. So the extra vector that you have has to be linearly independent. At least one of them will have to be linearly independent. It could be that there are more than one that are linearly independent, but at least one of them will have to be. Some of my students love to debate with me, so they will try to find edge cases to say that maybe this statement is not quite right. Here is an edge case for you. Suppose the extra vector is a zero vector. Then what happens? Think about it. Zero vector, as it happens, will not count in this argument because it doesn't help in spanning a vector space. One thing I would like to reiterate is the fact that the linear combination that you come up with for any vector in Rn with the n vectors that you have specified here, or any number of vectors really, but linearly independent vectors, is a unique one. If I give you 5 vectors in Rn and I give you 5 scalars in Rn, you scale the first vector by the first scalar and so on, then sum it up, you get only one unique vector. It is important to realize this because some of the proofs that will come later will depend on this. Let's take a different situation now. This is my example number 2. Example number 1 was when I had the blue vector and the red vector not on top of each other. It spanned all of R2. Going to number 2 now, I have two vectors, the red one and blue one. Can you see that they're actually linearly dependent? They are scale versions of each other. x2 is just 2x1. Now I can take some scaling factors, 1 and 1 to begin with. I get a third vector, a green vector, and if I plot it on this coordinate space, I see that that vector also lies on top of the line defined by the blue vector or the red vector. And if I keep scaling those vectors by different scalars and keep creating new linear combinations, all of them will lie on this single line going through the origin. What it means is that if I give you any green vector in this line, you will be able to come up with a linear combination of either x1 or x2 or both, so that the sum, the linear combination, actually equals the starting green vector. But that's only if the green vector is on that line. More than that, can you see that given any green vector on that line, you will be able to write it as not one unique linear combination, but any number of linear combinations. For instance, let's start with this particular z1, which was 4.5, 1.5. Turns out that you can get any number of possible combinations that will give me the green vector. So that's what I have written here. That is basically because x2 is just 2 times x1. So I can write my z1 4.5, 1.5 as x1 plus x2, or 3x1, or 1.5x2, or really 3 plus 2 times t being any number, x1, minus t times x2, because 2 times x1 is x2. So this term and this term will just cancel. So my green vector can be expressed as any number of linear combinations, and that actually corresponds to something that you already know, even though it is not completely obvious at this point. It is the situation where you have an infinity of solutions. Let me give you another situation that you already know, but maybe the connection is not there yet. Let me give you another green vector that looks like this. This is not in the line, the green dotted line. And now I ask you to find a linear combination of my red vector x1 and my blue vector x2 such that you get this particular green vector that is sticking out. Will you be able to do that? You won't be, because all linear combinations of these two vectors, the red one and the blue one, will lie on that dotted line, and this vector, the new vector that I gave you, is not on that line. So you will not be able to make a linear combination such that this y can be expressed in terms of x1 and x2. And this situation is similar to, and in some sense identical to, the inconsistency in a system of linear equations, as you have seen before. It's just that the connection between these two situations is not quite there yet, but you will get there very soon. So let me explain that using my slide rather than the picture once more. If you have two vectors that are linearly dependent in R2, one is a multiple of the other, the linear combinations of these two are going to be the same as multiples of either one of them, because one is already a multiple of the other one. All linear combinations for that reason will fall on the same line. Take, for example, some linear combination here, some numbers s1 and s2, I don't know what, but whatever it is, I can already write x2 as 2x1, and then I can pull out x1, and you can see that it's some multiple, that multiplication factor, the scalar is s1 plus 2s2 times x1. You could write it in terms of x2 if you want, but it's on the same line. It's on the line defined by either x1 or x2. For avoidance of doubt, they are the same line. So one vector, as you know, is not enough to span all of R2. It will span only one line. And two vectors, if they are linearly dependent, they also span only one line. It is as though you have only one vector. It spans only one part of R2, a line going through the origin. That is important too. Later, we will call that a subspace. Two linearly independent vectors are needed and enough to span all of R2. Similarly, going on to the world of Rn, you need n linearly independent vectors to span all of it. If they are not linearly independent, then you will span only part of it. In Rn, much like in R2, if you have only one vector, it will span a line going through the origin. It will span a line of vectors. Any vector in that line can be generated by appropriate multiples of this one vector. If you have two linearly independent vectors in R2, that will span all of R2. But if you have it in Rn, that will define a plane. Two vectors going through the origin in some direction, that will define a plane. And all linear combinations of these two vectors will be on that plane. It will not get out of that plane. That's what I'm trying to show you here. Here I made it simple by kind of extending my red vector and blue vector by just adding one extra component to it. But that component was just 0. So even though these two vectors are in R3, technically, they are in the xy plane of R3. The z component is 0. So if we take linear combinations of these two things, doesn't matter what scalar you multiply x1 with or x2 with, the third component of the linear combination will always be 0 because there's 0 here and here. You cannot get out of the xy plane. So I have shown you a few possible linear combinations here. This is my example 3, but this is probably not very obvious. So I have a visualization, an interactive visualization on my website, also linked in the textbook. So let's go there. So if you go to the website of the book, la4cs.com, somewhere below the links to the videos, I have visualizations there. This is a chapter 6. So I have chapter 6, linear combinations in 2D. So let's go there. It looks like that. So if they're linearly independent, I can change the scaling factors here just to see that I can span any vector in R2. So you can see that if I change my linear combination, I can get any point in this plane. In principle, really going to infinity in any direction. Now that is a linearly independent case. If you go to linearly dependent case, then you can see that regardless of what scaling factors you use, because your starting vectors were linearly dependent, x2 being 2 times x1, you cannot get out of that line, that green line. So that's what I wanted to show you. In the case of 3D linear combinations, which would be a lot harder to visualize in a static slide, this interactive view might be more interesting. So you can see that my green plane there is actually supposed to be the xy plane. You can rotate it, can make it stand in front of me. Yes, now I'm staring at it right down the z-axis. Then I can see that these guys are just moving around. But if I rotate it so that I'm looking at it edgewise, I can see that whatever scaling factors I use, the green vector is never getting out of my xy plane. So play with it and see that you're confined to the xy plane. Why? Because the z component of my two vectors is just 0. So whatever linear combination you take, the linear combination also will have the third component, the z component, to be 0, which means you're confined to the xy plane. So that was this one. That is my example 3. So all linear combinations are confined to the xy plane. Now I take a more complicated example in example number 4. Here, the two vectors x1 and x2 are not on the xy plane. There are some general vectors pointing in some direction, but it doesn't matter because there are only two of them. There will be one point in the coordinate space that is 1, 2, 2, that is the tip of my red vector. Another one that is 3, 1, minus 1.5, so there are 2 points. And then the origin, there are 3 points. They form a triangle, and a triangle, as you know, lies on a plane, and that is a plane that is defined by these two vectors, and all linear combinations will fall on that plane. That is a lot harder to visualize. So let's go back to our interactive visualization and take a look. So click on this general plane. Those are the two vectors. You can see that they are on some plane. It's still not obvious what that plane is. Let's orient ourselves so that we look at that plane of these two vectors edgewise. So I have rotated it enough so that the plane of these two vectors, x1 and x2, we are looking at that plane edgewise. And my xy plane also is, I'm looking at it edgewise. So I'm actually orienting myself in a specific fashion so that I see the edge of my xy plane and the plane defined by these two vectors that we started from, namely x1 and x2. So in this view, you can see the end of x1 and x2 being projected to the xy plane, and the z vector, the green vector, is a sum of the scaled red vector and blue vector. As I change the scaling factor, you can see the z vector also changing, and its tip is being projected to the xy plane. You can see that change. The most important thing to notice is that the z vector cannot get out of the plane, the green plane defined by x1 and x2. And if you want to see it from an angle, you can play with it. So do that and then try to understand how this visualization is actually telling you where the vectors will be. And it's very difficult to represent 3D on a 2D plane, and this is kind of the best I could do using a lot of vibe coding on Gemini or Ching Leela. Moving on, the bottom line here is that all linear combinations of x1 and x2 will lie on some plane, and it's the plane defined by x1 and x2 along with the origin. Just to continue with this a little bit, let's take 3 more examples in R3. This one, example number 5, you have 3 vectors, but look at the third vector, the purple one that we added. Can you see something special about it? These are actually all prime numbers, so that by accident we don't end up having vectors that are linear combinations. But here in this case, even though these are all prime numbers, the third component is 0 everywhere. Can you see that the third vector has to be a linear combination of the first 2? How do you see that? Just put them in a matrix. Columns of A, 3 by 3 matrix. What's the rank? Rank has to be 2 because you see a row of zeros down there. Or if you do Gaussian eliminations, you can have only 2 pivots because the third row cannot have a pivot. So the rank is 2. That means only 2 columns are linearly independent. The third column will have to be necessarily a linear combination of the first 2. So you don't have to know what the linear combination is. You know that it has to be there because now we know enough matrix algebra and Gaussian elimination, etc. to see this. What that means is that if you take linear combinations of all these 3 vectors, they will all lie on the xy plane. Now let me take example number 6 where you have 3 vectors, but this time I chose x3 carefully so that it is a linear combination of x1 and x2. So I know that if I did Gaussian elimination on a matrix containing these 3 vectors as columns, I will get rank 2 because I know that the third column is linearly dependent on the other 2. So I have only 2 linearly independent vectors, so the rank is 2. So I cannot get out of the plane defined by 3 points. 3 points, as you know, define a plane. This is my red vector, this is my blue vector, and the origin. And the purple vector will be on that plane. Finally, let's take one example where you have linearly independent vectors. So we go back to the vectors in example number 5. So instead of the purple vector there, let me take another vector that has some component along the z-axis. So this can take care of getting out of the xy plane. These 2 will take care of the xy plane. So you can span all of R3. That's the idea. So these 3 vectors are linearly independent. If you don't quite believe me, just put these 3 vectors as columns of a matrix and do Gaussian elimination. So 1, 2, 0 in the first column. This is going to be my first row. Scale the first row by 2. Subtract from the second row, you get a 0 here. So here this will be like -5 and this will be 0. And that is already in REF, row echelon form. Pivots are right here, 1, -5 and 1. So 3 pivots, rank is 3. The 3 columns are linearly independent. You can also see that there is no way you can get x3 as a linear combination of these 2 because x3 is actually the z-axis, a line along the z-axis, and the z component of these 2 vectors, the third component of these 2 vectors, is actually 0. And whatever linear combination you take, you can never get 1 as a sum of 2 zeros, regardless of what you scale it by, unless you're willing to scale it by infinity. So 3 linearly independent vectors are enough and needed to span all of R3. So let's summarize the 7 examples. The first one, 2 linearly independent vectors were enough to span all of R2. Now I'm using some green terms here and there. Those are things I haven't completely defined for you. We know these things already to a certain extent. So linearly independent, we know what that is. So 2 linearly independent vectors are enough to span R2, and more than that, 2 linearly independent vectors are needed to span all of R2. What R2 is a vector space. A vector space called R2 that is a collection, a set of all possible vectors of 2 real components. The span of 2 linearly dependent vectors is a vector subspace. We haven't defined that yet. That will come later today. But as you saw, these 2 vectors will span a line going through the origin. So it's a line of vectors. Moving on to example number 4, where we dealt with R3, 2 linearly independent vectors are not enough to span all of R3. They span only a vector subspace in the case that we looked at. This was an XY plane. Two general vectors in R3 will span some other harder to visualize plane through the origin. It's again through the origin. Through the origin is in red because that's an important constraint. Three linearly dependent vectors in R3, which is what we had in example number 5, also span a vector space. Three linearly dependent vectors would mean they are on the same plane at best, or maybe even on a line, but that would be a vector subspace, a plane through the origin. In the example that we saw, that was the XY plane. Three other linearly dependent vectors in R3, which was the situation we had in example number 6, also span a vector subspace, a plane going through the origin. This plane was a complicated plane, oriented with respect to all the axes and axis planes, but a plane nonetheless. Finally, in example number 7, we got three good linearly independent vectors in R3 to span all of R3, and any vector in R3 could be expressed as a linear combination of these three vectors. R3 is a vector space of all possible vectors of three real components. It's a set of all possible vectors. So vector spaces are sets. Now let's actually try to find some connections between linear combinations and our favorite equation Ax equal to b. So if I have k vectors xi in Rn and k scalars si in R, then I can define linear combination like that. Let's make some minor modifications to this. Instead of calling it z, let's call it b, and instead of having k, let's take n vectors, and let's say that each vector has m components. You can see where I'm going with this, can't you? And the n vectors, instead of calling them xi, let's call them ai. So if I have n vectors ai in Rm and some scalars, let's call them xi this time, in R, I can define the linear combination B as a linear combination of n vectors ai, each one of them is in Rm, so the linear combination also is in Rm, scaled by some values xi. So what is this thing? Let's put these ai vectors as columns of a matrix, and let's call that matrix A. Now A is going to have m rows because each ai is in Rm, and there will be n columns because there are n of them. So we got our original matrix back, and our x is x1, x2 up to xn. So n components there. So it's a member of Rn. And B now will be a linear combination of the columns of A by taking xi as the weighting factor. And that gives me m components because each one of the vectors ai has m components. You take linear combination, you get m components. And what do you have now? You have Ax equal to b. So the definition of a span is actually kind of embedded in our equation Ax equal to b. It's just that we used slightly different symbols for the entities there. This is an important insight, that this equation Ax equal to b is just saying that b is a linear combination of the columns of A by some weighting factors unknown at this point. Now let's define a few entities, mathematical entities, that will be useful, that we may have already used. Let's define a span of vectors. A set of all possible linear combinations of a given set of vectors is their span. So we start with a set of vectors, take all possible linear combinations, and that set will be the span of these vectors. So let me crystallize it by defining it. Let's take k vectors of the type xi in Rn and take any possible scalars, k of them, in R, and start forming linear combinations and put all those linear combinations in another big set. And that set, that big set, is called the span. How many vectors can you have in the span? As many as you want, because you can keep generating new and new linear combinations. So this is an infinite set. So span of set of vectors of the kind xi is a vector z such that it is a linear combination of these vectors that you start with. Of course, later we will use ai and n here and rm there to get back our equation. In set theory language, you have a name for the number of elements of a set that is called the cardinality. So that is k, that is the number of vectors that are defining the span, and that is the cardinality. In example number 1, we had two vectors. The span was all of R2. In example number 2, we had two vectors that we started with. That was the red vector and the blue vector. But the span was that green line. So this was example number 2. I had my red vector and my blue vector. I sat here and created all kinds of linear combinations. They all were on the same line, my green dotted line. So the span of these two vectors was only a line of vectors. That was example number 2. Now we went on to linear independence. We said that k vectors are linearly independent of each other if we cannot find any k scalars, not all zero, such that this linear combination is 0. This sounds a bit mysterious. This is not the way we defined earlier, but it's actually identical to that. So in example number 2, we had the situation where x2 was 2x1, the blue vector was twice the red vector, and we said for that reason it was linearly dependent because one was on top of the other. Now we can actually rewrite that to read 2x1 minus x2 equal to 0 vector. Now this linear combination of x1 and x2 gives you the 0 vector, but the weighting factors, the coefficients, are not 0. They are 2 and minus 1. So this is not a trivial linear combination. As a non-trivial linear combination giving you 0 means that the vectors are linearly dependent. So if you can form some linear combination of the k vectors such that Si is not all 0, at least some of them are not 0, and if that linear combination becomes 0, then you know that these vectors are linearly dependent. If you cannot form that, then they are linearly independent. Of course, if you take all Si to be 0, this will be always 0, but that's not the linear combination that we're looking for. We are looking for non-trivial linear combinations. Having all Si's to be 0 would be a trivial linear combination. In example 6, we explicitly stated that my purple x3 was this 3 times x1 plus 2 times x2. That means that 3 times x1 plus 2 times x2 minus x3 was 0. So 3, 2 and minus 1 as weighting factors in a linear combination gave me the 0 vector. So these three vectors were linearly dependent. They are not linearly independent. So this is the test for linear independence, and you will use this in your exams and tests and quizzes and stuff. Now let's take one more look at this dependence, linear dependence, and try to cast it in the same form as our equation Ax equal to b. Let's see what that means. Our original definition was this. Let me read this carefully. K vectors of the kind xi in Rn are linearly dependent if, for some Si in R, not all 0, we can write 0, the vector, is a linear combination of these xi's, k vectors xi. So the sums running from I equal to 1 to k with Si and xi, and that is a vector in Rn, but it's a 0 vector. If you can find that, then the vectors xi are linearly dependent. We saw a couple of examples of that in the previous slide. Now again, let's rename the symbols. Let's take n vectors rather than k, and let's call them ai. Let's make them members of Rm. And let's restate this. N vectors of type ai in Rm are linearly dependent if the sum running from 1 to n of xi ai, which is a member of Rm, is a 0 vector, xi being the scalar now instead of si. So the condition is that this should not be a trivial linear combination, by which I mean all xi's should not be 0 at the same time, in which case, of course, you will get a 0 vector, but there's nothing to write home about. Now put all these vectors in a matrix. We get the matrix that we know and love, A, which is in M by N, and we have a vector of unknowns, variables. We are saying that they should not all be 0, so it should not be the 0 vector, but it's a vector in Rn. And if we can write Ax equal to 0 with x not being the 0 vector, A, the vectors that we were trying to find the linear independence of, if this guy, this equation, has non-trivial solutions, then the vectors are linearly dependent. If the only solution this guy has is when x equal to 0, then the vectors are linearly independent. Very important to get that straight and know. Now let's give you a name for this kind of equation where the right hand side is a 0 vector in this case. That is called a system of homogeneous linear equations. And if you can find non-zero solutions to the homogeneous linear equations system ax equal to 0, then the columns of A are linearly dependent. Now this homogeneity, we are using the same word that we came across in the first chapter. So let's look at it a little bit. That's not part of this course really, but just to tell you, homogeneous equations of degree 1 would be linear equations. It's just that the right hand side would be 0. So a system of homogeneous equations would be of the type ax equal to 0. In degree 2, all terms in the polynomial or the expression that forms the right hand side of the equation, if the order is 2, so x squared, order is 2, x times y, x is 1, y is 1, so it is 2 plus y squared equal to 0. 0 is on the right hand side. So that is homogeneous equation in degree 2. So all of them should have the same power, combined power. Degree 3, of course, is an example. X cubed plus 2x squared y, so that is 2 plus 1, 3, minus x y squared, 1 plus 2, 3, plus y cubed equal to 0. 0 is important. The constant on the right hand side is okay because constant, you can think of it as x to the power k, where k is the degree of the homogeneous equation. It is actually related to the homogeneity condition that we started with. It's just that we were limiting ourselves to homogeneity in degree 1, which means linear equations. The output of the scaled version of the vector is the same as the scaled version of the output of x, then that is a homogeneous. That's what we said in our first class. So that is homogeneity in degree 1. In degree 2, it becomes x squared. In degree 3, it's x cubed. And degree k, it becomes s to the power k. And that is the reason why all of them should have the same power, so that this s to the power k can factor out. That is just the definition of homogeneity. It's not very important for this course other than the first one, of course, which was supremely important. The next video, we will go over these definitions of vector spaces and subspaces in some more detail.